sorry. Start? No, I guess sounds good. I think most people are in. Okay, so thank you guys. And it's been a fun week, and we're already we're halfway through. And so this will be the third of 4 lectures, and I'm very happy to be talking to you now about celestial amplitudes in proper. So what did we cover last time? Well, last time the goal was to show this equivalence between 2 corners of the IR triangle, which were basically saying that soft theorems are equal to ward identities. And in particular, the conclusion there was that we basically had this 2D current. So soft theorems being equivalent to ward identities landed us out on the very last kind of equation on the board or so, this notion of a 2D current. And just to remind ourselves, the U1 example that we looked at was, say, the leading soft photon theorem. We saw that the ward identity corresponded to an arbitrary angle dependence of the gauge parameter, where we're letting that gauge parameter be non-trivial at null infinity, and rather than just having compact support. And then the 2D current we got by basically restricting to some very special classes of gauge parameters, which were holomorphic. And then we had basically a way to look like at the soft theorem and see it as being an insertion. So I'm going to write an equation down in a minute that's going to look the same, but for gravity. So again, we focused last time on U1. This is in lecture 2. But from lecture 1, we saw that basically we know from the IR triangle it should generalize. So this IR triangle had a bunch of patterns, and so we know it should generalize. This should generalize. And so in particular, I'm going to go directly to maybe the third natural example. So if you follow basically, if you were trying to understand null infinity and null one fell swoop, maybe the easiest example wouldn't have been this U1 case, but would have rather been the supertranslation symmetry. And then this kind of triangle of relations between soft theorems, asymptotic symmetries, and memory effects led to a new iteration, which is the subleading soft graviton. So I'm going to look at that example for a minute because it's going to be the closest thing that's going to motivate celestial holography. So the subsoft graviton, the analog of this U1 current, this Kac-Moody-like current, is instead a 2D stress tensor. And what we mean by that is something very much coming from the bulk side. So we're going to define this object, which suggestively will be called TZZ. But in practice, we should think of this as a definition of what particular mode on the right-hand side we're looking at. So it's some prefactor that's less important for what follows. Smearing over the celestial sphere. So the fact that it's not local is a little bit of a fun kind of puzzle that people were running into for a while. And then a particular U moment of the metric. So let me just pause for a minute and point out that by C here, I'm talking about the shear. And so it's a particular leading, say, either like lower W bar component of the metric. And then by doing this U integral, I'm trying to kind of isolate not the Weinberg pole, which is a 1/omega pole, but the next subleading term with this kernel in the U integral. So that's what it's doing. But now once I've defined this guy, then every time I look at a soft insertion, so basically I have a scattering amplitude and I have some graviton in that either the in or the out state, and now I'm going to take that graviton integrated in U, or the Fourier analog of it, and smear in the sphere. And I'm saying that then that amplitude looks like it takes the following form. So TZZ O1 at On is a sum over K of HK C minus ZK squared plus d by dzk C minus K O1 On. So the stripping off is what we would expect from a soft theorem, because we know that for these soft theorems, basically the amplitude with an extra graviton is proportional to amplitude without it. So the structure of the endpoint for Zen plus 1 point is consistent. And then this kind of art, or this like funny combination, is exactly to turn it into the form where it looks very suggestively like a 2D stress tensor. But what I want to point out is that this HK is actually still a differential operator. So it's basically measuring the Rindler energy and the spin. So let SK basically be the helicity, and then omega k is the usual energy. This guy is not just a number, it's really an operator. And so,
What is capital C?
Oh, so this capital C is roughly limit as r goes to infinity of 1 over r h cz, where h is the metric, or different from flat or whatever. So you can put g there, sorry. Okay. So the point is that this differential operator is going to be diagonalized for boost eigenstates. Okay. And so, as the story goes, roughly we can just choose to say, well, I'm going to take each of my in and out states in the S matrix and call them some operator, and then as soon as I do, it looks like I have this form. But now I'm motivated further to talk about scattering in a very particular basis. And so the goal of today is going to be to see how the kinematics of scattering lead us to these objects called celestial amplitudes, which are basically the kind of translation of the bulk's perturbative scattering to the celestial hologram. So let me write that down. Kinematics of scattering. Are going to lead us to celestial amplitudes. Okay, so the underlying claim of, I guess, this program, and especially, I guess, my talk today, is that these symmetry enhancements we saw in the first two lectures are naturally pointing to a codimension 2 description of scattering. So this symmetry enhancements basically tell us the S matrix is naturally organized as a CFT2. And for most of what I'm saying today, I could actually just go to any dimension bulk and then a codimension 2 celestial CFT. Obviously, there's some situations where, like for example, superrotations, where like in the structure of this Virasoro symmetry versus the global guys is going to be different in 2D. But let me just emphasize that most of what I'm doing, besides what I'm going to say right now, would generalize to the higher D case straightforwardly, because again, we're just playing with Lorentz invariance, and that's going to be one thing. So let's just keep that in mind. This SL2C, which is up to some like quotients, Lorentz group in 4D, is a subgroup of Poincare. And this subgroup corresponds to this 2D global conformal. So basically, in the picture that I gave for the public talk, the going into warp drive or whatever, this like very like highly boosted observer, that's supposed to be showing how the Lorentz transformations that we're used to would act on the night sky in a way that actually is like doing a global conformal transformation. And the point that we see with the soft theorems is that once we add gravity, we're no longer looking at the isometries of Minkowski space, which is Poincare, but we are now going to basically, let me make this a little shorter so I have space. We are now going to these symmetry enhancements like the BMS group, which can include superrotations depending on how you want to define the angular part. And that those guys are now much larger symmetries. So we have that Vir cross Vir, which is some definition of superrotation as a subgroup of BMS. And of course, this is the same Vir cross Vir here. But in particular, we have like larger symmetry multiplets. And that's the point. So again, the point would be that right now we might be trying to distill the kinematics at our disposal, but in the same way that in a 2D CFT, you could try to organize things in terms of Virasoro blocks versus global blocks. It's interesting if you can have more of your states be related. So in particular, what I'll set up today is going to be the Poincare primaries and then various descendants from the point of view of this BMS story would be like extra collinear or so or soft gravitons being added to that state. So now the rest of this talk is going to be explore the following object, which is the claim that if I just look at my standard S matrix element, but in a basis labeled by the fact that I want them to be boost eigenstates, then that object is the correlation function that I've been very glib about, just kind of saying it's fine to treat it like it is. So there'll be some index for in and out, some location in the celestial sphere, etc. And part of the goal of what I'm going to talk about now is to unpack exactly what the different labels mean and what their ranges are, etc. So this is just a change of basis. And so on the one hand, that means that we shouldn't be scared. We're just basically trying to take our scattering matrix elements, change the basis for that scattering, and we know we can do it. We know we can artificially have a 2D CFT just by the definition of the fact that we have a Lorentz invariant bulk theory. And so again, the thing to be concerned about would be, what's the utility of this? Are we going to make our lives harder? Are the amplitudes simpler in momentum space? So why you're doing whatever integral transform you need to do to change that basis. And I think that's a good challenge, because the point would be, again, the hope is that in this case, it's the symmetries and the organization in terms of symmetries that's telling us to do this. And I think between this talk and the next talk, we'll at least see some examples where there are symmetries, at least of certain features of the story. So for instance, in the OPE, or these collinear limits, that we would not have maybe guessed from just the momentum space amplitudes. But then again, the W infinity story that is going to be kind of the punchline of tomorrow's talk, maybe also could be understood by twistor people. So we can be careful there. Okay, so now I'm just going to start with the global part. So let's forget about all the fun stuff and do this silly thing of just looking at Lorentz invariance and going forth. Global part. And basically, the point, I'm going to treat this two ways. The first way is going to be in terms of preparing wave packets, and the second way is going to be in terms of the single particle states. And I'll explain why it's good to see it twice, because on the one hand, it's a little easier for generalizing to massive or whatever if you just know how to prepare the wave packets. But again, this is just kinematics, and this is just Lorentz invariance. So we can just choose to prepare our scattering states that are 2D primaries. Like by a convenient choice of wave packets. And then I'll put a definition here, which I guess depending, I mean, it's not super formal, so it's more of a term of art within this little celestial community, so don't freak out over if you don't want to remember it. But for my definition, I'm going to say that a conformal primary wave function is a function on the bulk space-time. So in this case, I'm going to stick to R1, 3, which transforms as follows. It's and a reference point, W bar on the celestial sphere, which transforms under SL2C as follows. So I have a label for the bulk spin. So say I have a spin 2 particle, and I may, depending if it's massless or massive, have different helicity states or spin in a given direction, labeled by J. If I do a Lorentz transformation on the space-time point and simultaneously transform the celestial sphere, so in this case it's nice to use coordinates where it's just a Mobius transformation, but you could also do this with in higher AD if you needed to. And same thing with the bar. This guy picks up some weights. And then there's some, let's say, times a whatever action on this spin index here, the representation of the Lorentz group the field is in, acting on phi. So if there was any vector index, because this is like a gauge field, that would be in there. So I'm basically saying, let me try to construct some functions on my spacetime that have this nice covariance property with respect to roughly what you can think of as like a bulk to boundary propagator. There's a point on the celestial sphere. So there's a point W, I guess, living on the celestial sphere. There's a point X in the bulk spacetime. And now, for what I also care about, so here I also want to impose the EOM. So basically, if I was interested in a scalar field, S would be 0, J would be 0, and I would impose, say, box of phi on the x coordinate is 0. And so then if I have that, with just those requirements, then using the symplectic product, I can construct an inner product on solutions in my phase space. So basically, Lorentz invariance of this inner product, my inner product, will guarantee that the object O S plus minus delta J is a function of only the celestial sphere that I get by pairing a bulk operator at point X with this conformal primary wave function appropriately conjugated. And about that inner product on some Cauchy surface. So. Is a 2D primary operator. So basically all I'm saying is that I am choosing a wave packet, and instead of asking that wave packet, for instance, for the plane waves, behaves nicely, it just picks up a phase when I do a translation. I'm asking for it to behave a certain way when I do a Lorentz transformation. And then now, because it depended on 2 points, there is the x coordinate in the bulk, the celestial sphere coordinate. The inner product is basically taking an operator in the bulk and smearing it with this wave function on a Cauchy surface in a way that basically removes now the x dependence and leaves me only left with the w. But because under a Lorentz transformation this transforms, and I can move it to how the operator should transform under Lorentz transformations, I can basically eat that up, and then this guy will transform just as the w coordinate does, and it will be a primary field. So that's what I'm doing. I'm basically using Lorentz invariance and a nice choice of wave packets to get me some operators in terms of the bulk operators that transform with celestial primaries. And now I can basically go forth and do this, whether or not I want this to solve some massive wave equation or what j I want compared to s. It's fine, but my task for you, or for now, is, okay, I can say I can do this, and it looks like I can do this, but I haven't given you these functions. So I'm going to spend one more board showing that it's not that hard to construct these wave functions that behave nicely under Boost. Did I make that hard for myself? Let me push it up a little bit. Nope, nope. Yeah, of course. The w, yeah. But it's not as scary because the analog of this would be for a momentum space wave packet, right? You have x as a space-time point, and you're labeling it by an on-shell p. And then p has an energy and then a direction. So it's the same thing. And we're going to see very shortly that basically that on-shell, the space of on-shell guys is going to be in delta and that direction. And so, right, you can kind of, I think that there's one slide at the end of Clifford Chung's talk at the Bohr Institute from last year, where he's trying to kind of make the analogy of what is the plane wave compared to a bulk to boundary propagator in ADS CFT. So it's nice. So now let me just say that this isn't that hard. Oh yeah, the question's good.
Is this inner product roughly the Klein Gordon inner product?
Yeah, so it's supposed to be the higher spin, general, or a general spin generalization of it. But honestly, I think the easiest thing would be just to start from the symplectic pairing, and then I'm even undoing the complex conjugation in the inner product here. So yeah, I think just start from the kinetic term in the action, and find the symplectic pairing, and then use that. It's fine.
Okay, and the choice of sigma?
Yes.
Does it matter?
So depending on the definition, so I think the point is that right here we're only looking at kind of the single particle state being prepared on the vacuum, or I guess I would personally say that there's one subtlety with the kind of in and out labels. Right now I could try to select A or A dagger from either the in or the out Cauchy surface, but if I wanted to be more glib, maybe I would say by out I mean put the operator out at future null infinity, and I put it at past null infinity, and then let the state that I've prepared select either A or A dagger for me. So I would say right now this definition doesn't depend on sigma, but I would be sympathetic to someone saying that by out operator I mean just put the operators, these same constructions on the light sheet that is future null infinity instead of past null infinity, and then go from there rather than, yeah. So it doesn't matter, but it might if there's other operators there, right? Yeah, good, okay. So if there are no more questions at that point, so I'm glad that people questions is good. So this isn't that bad. So it's going to be easy to construct. And so what I'm going to write down is just using the following, basically, two vectors. So I have my reference vector, which we can think of as basically a direction for a null momentum. And then I can create polarization tensors, and I'll just write one of them in terms of a derivative of this Q. And I want to point out that even if I was going to deal with a massive particle, I would still try to label things in terms of a point kind of on the boundary of the on-shell hyperboloid. So I can solve massive wave equation in X, still in terms of wave functions that depend on a light-like direction Q. But maybe I should have done that aside after I write it down. So from this guy, we can construct a null tetrad. follows. And the point is that I want to build up objects just in terms of the bulk spacetime point and this reference vector and the polarization vectors. So that should be enough to span the tangent space of a manifold that have definite weights. And for most of what I'm going to do, I'm going to ignore a lot of these, like the n component of the tetrad, and not write down the m bar. But the point is just that I am basically using the fact that I know x is a vector. So under Lorentz transformations, it just gets multiplied by lambda. But if I look at q and I basically do the Mobius transformation of w, I'm not going to quite get a Lorentz transformation. I'm going to get an overall factor. And that factor is precisely what makes it have that CW plus D dependence out front. So basically, my claim is that if I use these tetrad elements, then we have the following form. Wave function that's radiative. We have phi s of delta. And I'm going to look at the j as plus s example because that's like the other guy is just the complex conjugate. And if I wanted to look at different spins, I can just kind of either take derivatives or whatnot. We'll not worry about that for now. So I have some tensor product of, or products of these m's and some function of x squared, which I would basically try to solve the equations of motion that I want to impose to figure out the form of that. And for the ones I'm most interested in, it's just one. And here. So basically, this combination of q dot x is giving me the weight of the field. The m's are not changing the weight, but are giving me a non-trivial spin. And then the shadow wave functions, or the original ones that I'm going to talk about now, which I call Mellon transform, but there's no reason for you to realize that it's called that, are basically different profiles in x squared here. So basically, the reason why I wanted to talk about the wave function approach is that basically this wave function setup naturally generalizes, or naturally covers, both the m is 0 and non-zero cases. M equals 0, and m not equals 0. But what I want to talk about more in detail is that basically for m equals 0, things are going to be simpler. So for m equals 0, I can kind of have a quicker route with only one integral to take me between the two bases. And so what I'm going to write is the following. So let's look in particular at the gauge field that kind of started our story with the U1 example. So say I look at the positive helicity guy, and I leave the plus or minus label here for now, but at some point I'm going to just drop it because I don't care right now. So I have one copy of m out front of q dot x delta. And the nice thing about it is it turns out that up to some coefficient that's a function of delta, which I'll care less about because I just care about the covariance properties, but you might care about where there are poles, etc. This is just the usual polarization vector times a Mellon transform of the plane wave. Up to a gauge transformation. So if things are really gauge invariant, then I should be able to drop that. One might be a little bit wary about the, again, large gauge transformations. But modulo gauge transformations, these wave functions that I've tried to so delicately construct so as to transform covariantly under the Lorentz group in a certain way, really can just be thought of as I take my momentum space guys and I Mellon transform them. And that's going to be great because now we can just Mellon transform our single particle states, or even the S matrix elements directly. And so just to be, because I guess I sometimes take this for granted, this transform here is the Mellon transform. And so unlike in some of the CFT literature, there's Mellon transforms in the Mandelson invariance. Here I'm doing it on the external energies. So what I'm going to do right now is we're going to look at, so let's look at the following state. Labeled by weight delta, a direction in the night sky, which is the North Pole, say. And this is just going to be a superposition of the single particle states with momenta in a given direction. And so we know how we expect the Poincare operators on our Hilbert space to act on the single particle states that are appearing in this sum. And so, for example, in particular, one light cone momenta, the one that's P0 minus P3, is going to be 0 because 1 minus 1 is 0, as is either combination of P1 plus or minus I P2. So they're going to annihilate. State. So let's now also look at the Lorentz group on the next slide. Okay, so while the combinations L my chalk is slowly dying. So I'm making these combinations of Lorentz generators for convenience, and together they should span my 6-dimensional Lorentz group in 4D. And so I guess writing them out might not be as illuminating, but I have it written down, so I'm just going to go for it for the timing. But the point is going to be that roughly some combination of these will naturally annihilate the state because they are in helicity representations and not in continuous spin representations. And that will be precisely the highest weight condition that we would be used to in a 2D CFT. Okay, and so one thing I just want to keep in mind for those is that Ki here is Mi0, and Ji is 1/2 epsilon ijk mjk. Okay, let me grab check that's longer. I have it here. Okay. So basically, this combination obey 2 copies of the Witch algebra. And they act as follows. My state. So we have Lm, Ln is m minus n, L, n plus m. Same thing with the bars. Well, they're mutually commuting. And acting on my states, I have that I diagonalize by doing that Mellon transform. The L0 and L0 bar. While the L1s are going to annihilate the state. Okay, good. So what I want to point out here, so I guess that the thing in the corner here is the important punchline. Basically, the fact that if I were in a boost eigenstate, or sorry, in translation eigenstate, I would have still those 3 translations annihilating things, but I would no longer have a diagonalization of the L0, which is the HK in that slide. And then the highest weight condition is coming for free in some sense from the fact that So the little group of, I say, a fixed null vector. So like the reference momentum, which would be, say, omega is 1 or omega is omega naught, some reference guy. If I do the ISO2, the translations of that little group transformation, those should be precisely some combinations of the L1 and L1 bar that are making it a highest weight state. And so that's kind of nice that that's there for you. And so the only thing I've done is basically smear the energies or superimpose states of different energies to diagonalize at L0. And so now I want to make some comments about this story as follows. Erase this stuff. Any questions while I erase the board? I'm going to try a little bit. So the first comment that I want to make is about the spectrum that we see. So originally, if I had a single particle state in my Hilbert space, I want the energies to be in the positive real axis. And so when I'm trying to trade out the energy for some conformal dimension, I don't want to be losing information. And so what I basically will see is that there's still a continuous spectrum, which is the harbinger of the fact that I needed a full extra null direction to capture my radiative state. And so the spectrum seems to lie in the principal series. Spectrum to capture the radiative phase space. Now, another thing, which is kind of confusing, so if I argued that, okay, if I look at the wave packets with those values of delta, right, they have this q dot x here. X will go basically like the radial coordinate. And so that guy to a power that's 1 plus or I lambda, at least is like kind of a radiative 1 over r fall off, say, for the scalar field where there's no m's here. And so that looks nice. But now what's going to happen when I try to act with a translation? So what it naively looks like is that if I take my other translation generator, which is the one that doesn't annihilate that reference direction, that would shift delta goes to delta plus 1. And so that ruins any statement I was trying to say, but, oh, let's just use the principal series spectrum. And if anything, this caused some confusion in the, like, kind of the early days of this literature. And so here were dragons, at least, if not still. But so for what I'm going to talk about in what follows is it won't matter because, the point is going to be that I really want to look at how these amplitudes behave as a function of delta, and if we continue to the complex plane. And then I'll be interested in particular in how translations act on various couplings between these modes as a function of delta. And there's going to be a lot of nice structure there that we're going to try to unpack more in tomorrow or Friday's lecture. And so that's just two things about the spectrum to be careful about. And basically, the next thing that I want to point out is that so far I've talked about, okay, so we have these single particle states. They're in the boost spaces. They transform nicely under Poincare. But the whole point of the story was that I had started from talking about these enhanced symmetries. And so, for example, in the Virasoro case, it's easy enough to try to just take these values of m and n and extend them beyond the -1, 1, 0 to all integers, and then we get the Virasoro guy. But now we know that while the subalgebra would correspond to our usual Poincare generators or realized say by these vector fields on the celestial sphere, we know that the interpretation for the higher modes is going to be that there's some graviton mode. So the soft graviton is going to be appearing. And so you're going to basically be organizing like the kind of multiplets of these symmetries acting on a given state are going to include extra gravitons acting on that state. So that's going to be nice. And so let me add that as another bullet point. So we talked about Poincare primaries today. But we can just as well extend this to BMS primaries. And we do so by basically extending the range of these operator algebras, like the index there, and then knowing how to construct those generators from the soft gravitons. And so Banerjee's papers are a nice reference for that. So these are multiplets with extra soft gravitons. And I would recommend CF Banerjee's results. Papers from a couple years ago. Okay. Yeah.
Quick question. So
No, absolutely.
Yeah, so these eigenstates, these Bose eigenstates, they all have some singularities, right? So do they form a basis? Like can they actually be like a transmove solution of field equations?
No, so it's actually good. So what I want to say is the kind of cute thing, and this is maybe like we're going to write it out a little more carefully. Maybe not none of these lectures, but I'm saying like this, like some paper where like it's been plugging it. So the argument for the fact that is it principal series or is it highest weight, right? Basically, the principal series story. The reason why there's this confusion in literature is because there's a statement that principal series representations don't have a highest weight state. But when you say it doesn't have a highest weight state, you're talking about in like an L2 sense. And so you really want to be smearing things in the sphere. And so basically the inner product for these single particle states is just a Mellin transform of what we're used to, which is a distributional one. And so these are principal series reps. They're basically distributional elements in this these states. And so I would say that they're not you're right that one should be careful, and I would say that you should properly smear these operators in the celestial sphere to talk about states with a well-defined inner product under like the norms you would talk about in the principal series rep. Is that like kind of what you're asking, or you're worried about the space-time singularity? Oh, okay. So I'm thinking about one. So from the space-time point of view, there are indeed going to be possibly 2 points where you can have an issue. One is the light cone of the origin, and the other is the hyperplane where q dot x is 0. And formally, there's an I epsilon prescription kind of hidden in this x plus minus that's helping us avoid it from the point of view of where the real like space-time locus that we care about is. But I think it is interesting to think about where those things are. But in the end, they're still coming from basically doing the Mellin transform on the plane waves with a regulator. And so you can see that, I guess, unless we added that epsilon, you wouldn't have the energy integral in the upper right-hand corner there converge. So, but formally speaking, the inner products are still okay, like in the sense that like if you had p prime and p, this would be proportional to like say delta cubed of p minus p prime, which so is distributional, and then doing the Mellin transform on both sides. So compose this with omega and the omega prime. And V star would basically give you a delta of like lambda 1 minus lambda prime and delta 2 of the p hat. So it's just as distributional, but I agree that from the point of view of the spatial perspective, the wave functions look bad. So the inner products in them are manageable in the same way that the inner products in plane waves are distributional, but I agree that there are singularities that you could be worried about how you're avoiding. Any further questions? Okay, so let me I want to then write one more thing down, and we can either chat more about it, or I can go a little bit into the preview for the next lecture. depending on how we want to use our time, which is as follows. So basically, given what I was saying about the single particle states, I know I can just can Mellin transform the amplitudes directly. And so basically, what I want to say is the following, is that what I'm interested in is this object on the left-hand side, which is some celestial CFT correlation function. I'm going to drop the spin here for now because it doesn't really matter. And if somebody's taught me enough about amplitudes, whether it's coming from the twistor theory perspective or from like Taylor's perspective, then I don't need to try to just, I guess, bootstrap or start from consistency up to what these correlators look like if I was following CFT lectures. I would just instead start from the amplitude that I know and do a Mellin transform on it. So basically, integral infinity. Right, so basically this object is a thing that I know. This integral is something I have to do, but at least it's just one integral for every leg. Then I have the object that I know from what I've constructed on these other slides or boards is a correlation function of primaries precisely because of that ISO2 helicity representation statement about the single particle states. So now I have this object that is a 2D CFT correlation function by design. So it's literally the kinematics, let me do it. And then from there, if I really do have a CFT, I can start to build my dictionary. So basically this equation is going to be what I use in the following lecture to go forth with the dictionary. So this is going to be the starting point. This is going to be basically the key to the dictionary. But maybe what I want to just close on, besides that being the thing, is maybe debate or pose to you exactly maybe what we would expect. Okay, so maybe I can turn it on you guys. If you said we're studying a CFT, what would be the things that I would want to go forth and try to bootstrap? I need this operator spectrum, and I need the OPE data. So can we try to guess, or maybe I don't want to be too interactive because it's the end of the day, but if we wanted to try to guess what those would be, well, we have our single particle states. We know what the spectrum I needed to capture the on-shell states. So in momentum space, this was an energy and a direction in the night sky. And in the case of, so let me, so basically, in the case of this story here, I now have a continuous boost rate. So maybe that's weird from a 2D CFT perspective, but it's just there. I know I have to have it. And I also need to have larger symmetry algebra, so I have Poincare that shifts that spectrum. So basically, my spectrum, I have some handle over. So if I had a 2D CFT, I would use symmetries, use my symmetries to build my correlators. If you hand me first this operator spectrum, and two, the OPE data. Now, one thing weird about the fact that the celestial CFT is this dimensional reduction of scry is going to be that the correlation functions look a bit singular as far as like they're distributional just because of translation and variance getting in the way. And the operator spectrum is this continuous like principal series. But in practice, we know what this is from basically the statement that we're building up from these on-shell states. P is a function of omega and say some direction of the night sky. Gives us this delta in 1 plus I lambda. And then, so that answers 1. And then the second thing that we also know is what would an OPE be? So the OPE would basically be if this is really my celestial CFT and I have my 2 sphere and I have 2 operators and I want to say bring them close to each other and then expand in a radial quantization picture and replace that with other operators at the North Pole, then I really want to be interested in the collinear limits of scattering. So basically, the kind of thing I'm presaging here is that somehow the collinear limits of scattering should be encoding this celestial OPE data if I really did have a 2D celestial CFT. And so roughly the program of trying to bootstrap a celestial amplitude would be to bootstrap scattering amplitudes from soft and collinear limits. And so I think, although that still gives me like 10 minutes technically of time, we started probably a minute or 2 early. I'd rather like close with that food of thought rather than go into some of that dictionary. But the goal of the next lecture on Friday is going to be, we're going to push forward with these different ingredients of the celestial CFT, start to build the dictionary that I've advertised above, or here, right here. And then from there, we'll see that we uncover even richer symmetries. And so to basically say where the lectures are going to go at the final thing in the end, it's going to be these asymptotic symmetries pointed to an angle-dependent enhancement, gave us these 2D currents. Then we kind of ran with it from the subleading self-graviton, diagonalized the boosts to get us to a 2D CFT where the operators really do look like they're 2D primaries. We try to treat it like a 2D CFT where we then have this question of what's the operator spectrum, what's the OP data, can I try to build correlators from that, or what subtleties do I run into? And in doing that and analyzing these like collinear limits, we're going to find even richer symmetry structures if we take this radial quantization picture seriously, which is going to be the W infinity story that might tie in nicely to the Twister people's lectures too, but maybe not. But yeah, so thank you guys. That was for today. Question? I think I saw your hand.
Even in the most optimistic perspective,
Yeah.
could you hope to get the OP data for massive particles in the bulk, or would you just have to guess it?
So I think, so that I still, like I lean hard into the bulk space-time perspective and being near the boundary. So I think that you can talk about OPE data maybe for massive states like near an hyperboloid near I plus. And then from that, I would do the integral transforms to the boost ones in the same way that if I was doing the story in the massless case, I'd start with operators near sky plus and then do the integral transforms. So I would say that there's a sense, okay, I mean, I'm really biased by trying to, I guess, view things in terms of a 4D free theory a little bit too much. And there, I think I should be able to do something for the massive story. And then I don't have good intuition for how it's going to interplay with the celestial transforms, which is basically trying to push everything on the mass shell hyperbola. Let me like draw a picture here. So we're taking the point near I plus and roughly treating it like this hyperbolic foliation of de Born-Slodukin. So maybe some point here and point here. There might be some operators, but I do this bulk to boundary propagator smearing that basically makes the wave packet very much peaked near one of the points in this boundary celestial sphere. And then the question is how does the celestial version of that OPE capture what features of maybe an OPE I would have here? It's less obvious versus for the massless case, at least the collinear limits, like being local on the celestial sphere is also kind of more manageable from the point of view of scry because you're at least at the same null generator. So I don't have a good intuition for how that's going to interplay, but I feel like I could try to to force the things that I would do on the null case and see what happens. And if I did that, I would try to start from looking at the behavior of two operators on the future light, future I plus hyperboloid, but I don't know.
And why would you guess the story is going to be similar to something you would get from free fields?
Because, okay, so I guess I don't know if I can say that for the massive case, but I'm trying to, like, why I want to build it up is because in the massless case, there's all these issues of like OPE, associativity and whatnot, and it's just like, I know these operators are acting on my bulk Hilbert space just as they're acting on the radially quantized one. And so if that makes sense, then operator ordering shouldn't matter unless there's something funny about the fact that I've smeared my operators in a certain way, and now either those integrals don't converge or that's the subtlety. So I like to go to the 4D case because in each situation, like I can view the S matrix elements. These correlation functions aren't just amplitudes. I can use a extrapolate dictionary for the amplitude and say that they're correlation functions in the bulk. So my celestial correlators are basically dimensional reduction of bulk correlators. And then I can talk about OPEs in the bulk, just as I can do it in the boundary, and that's where, and then if I don't know the theory in the bulk, maybe I can talk about the, so in the case, I actually don't think I would have a good handle of the massive case in that case, because you're answering the question for me in the sense that, talking about the OPE of free massive field, I don't know how to necessarily handle that, but because it's not a 4D CFT. But in the case of the null guy, I can use that intuition. So now I'm saying I don't know what I would expect in massive, but it's fun to think about. Sorry. Yeah, no. Sorry, I was just talking my way through it. And I don't know if that applies. So, okay. Good. Adam?
I have a dumb, unfair question to ask.
Oh no, go for it.
Massive question.
Yeah.
So, for the collinear limit of massless fields,
Yeah.
there's some intuition for why you might expect to get something because there's some universal feature called scatter.
Exactly.
But for massive particles, you expect the mass to regularize any IR divergence. So, is there something one could hope to get from collinear limits of massive particles?
So what I want to, I'm trying to think why I am still confident. Okay, so the reason why I'm confident that some of the story goes through, and again, so I want to backtrack because the thing I was saying about the OPs and CFT stuff won't apply for the massive guy, I think. But the thing that will still apply is that I have the algebra of the fact that the gravitons are coupling to either the massive current or the massless ones. And so I know that there's upcoming papers by both Alfredo and then Himwich and Pate, where they're basically talking about the soft theorems for the massive guys. And my impression is that I can still just mechanically construct operators that would couple to the soft gravitons with the collinear limits and realize the symmetry algebra on the massive phase space. So I think I can build up operators that basically are taking in the momentum space picture the fact that when I go soft, I'm like kind of local on that on shell hyperboloid. So the massive particle emits a soft graviton but doesn't change its momentum, and then build up like quadratic like A dagger A operators that realize the W infinity symmetry from the massive guys in the same way. And so I have kind of a realization in the massive phase space, I think, of the like wedge truncation of W infinity. And so that already sounds like I can fit the massive story into the celestial symmetry pictures, but the symmetries aren't coming from collinear limits of the massive particles. They're coming from collinear limits of the gravitons that couple to it. Like I'm copying out, but I know I can couple consistently to massive fields the things that I'm interested in symmetries. So, but I don't know about the OP itself, like from the way I was trying to tell Adam. Okay. I like unfair questions. Those are more fun. Okay. Any further? Was there another question?
Sorry, no,
Yeah.
That's a very basic question.
So what's f of x squared in the numerator?
Oh, yeah, sorry. So I left it there for fun because basically, if I'm just saying Lorenz invariance, then I could put any function here. Normally, it would just be 1 for the Mellon transform guys. We're like up to a constant of delta, like I wrote up there. But it could be also like x squared to some like whatever is it, d minus like delta. So Basically, there's two solutions to the Klein-Gordon equation, for example, would have two independent solutions. One of them is a shadow transform, but that doesn't affect the weight. So I was leaving it because it's a free function of x squared, and also if it was a mass, I would solve for that guy, and it'd be a mass dependent. So, yeah. Okay, good. Well, at least with the questions, it was perfect timing, so I timed that fine. Good.
Okay, just a reminder, we have this pizza night, not quite night, but at 6 we meet, hopefully as many of us as possible.